Hi there, my name is Peter Murphy and I'd like to welcome you to CNA's Manufacturing Technology Center, or MTC for short. Now, before we get started, I'd like to talk about some key considerations when it comes to safety. One being, whenever we're down in the MTC area, we always wear our protective eyeglasses and steel-toed anti-slip safety footwear. Overalls, although not required, are recommended as some of the work on the machines can be quite dirty. Today, I'm going to be showing you how we set up our G54 work offset command on our Mazak Vertical Center Nexus 410A-II. This CNC milling machine has two necessities in order to operate. The first being an air supply, and the second is a power supply. So come with me now while I show you where we can find the air supply and the main power switch for this machine. Now the first thing that we want to do is come back to our quarter turn ball valve here on the wall. What we do is slowly turn the handle so that it's in line with the pipework. Then we confirm on the regulator pressure gauge that the pressure is 120 psi. Next up, we have to locate the power switch located at the back right of the machine. And we simply turn the switch to on. Now that we have air and power supplied to the machine, we need to power on the Mazak's controller. We do this by simply pressing the green power button to the top right hand corner. Next up, I'd like to talk about some of the major components of a CNC milling machine. The first being the column. The column is this section of the machine here which houses the milling head, the spindle, and other critical components. Next up, we have the spindle. This is the rotating component responsible for holding and rotating the cutting tool. The spindle speed and direction are controlled by the CNC system. Next up, we have the tool changer. In mills with automatic tool changers, this component allows for automatic exchange of cutting tools during the machining process. Let's see it in action. Let's do another tool change so that I can show you what a flat end mill is, a very common tool in the CNC milling process. Here we can see a flat end mill. The flat end mill is held within a tool holder, which is inserted into the spindle. Spindle then rotates this cutting tool so that it can use its cutting edges to remove material. Next up, we have the table. This is the work surface on which the workpiece or vise is secured. The table can move in the X and Y directions. On this machine, the spindle moves in the Z direction, taking care of depth. Next up, we have the controller. This allows an operator to input commands, load programs, and control the CNC milling machine. Next up, we have our cooling system. This consists of a pump and a reservoir. A cooling system is a system that provides coolant to the cutting tool to dissipate heat and improve cutting efficiency. Let's see what happens when we turn the coolant on. Oftentimes when we create a CNC part program, we're forced to use more than one tool. And because for different purposes, sometimes we need to have tools that are longer than others. Because of this, we need to inform the CNC machine of the different lengths of each tool. So how is it that we can determine the length of a tool? Well, that's right, we have to measure it. And to do that, we use a height gauge. Now that we've taken a length measurement of our flat end mill using our height gauge, we need to input this information into the controller. We do that by selecting the tool data window, scrolling down to tool 8, which represents the flat end mill that we measured. We then need to press length offset teach. Select the length window, which displays a graphic showing the measurement that we took using the height gauge, which measures from the bottom of the shoulder of the tool holder to the top of the flat end mill. Now I measure this length as 4.838. So that's what I'm going to put into our length from gauge line field. I then press input, and this has updated the length of the flat end mill in the controller. Now, before we go any further, we need to talk a little bit more about safety. Because we'll be entering the work envelope of the machine to set up our workpiece and set our G54, we need to immobilize the machine so that it's safe to do so. Now, with the door of the machine closed, I'm free to move the table in the X and Y directions as much as I'd like. However, with the door open, because the door is safety interlocked, if I try to move the table in any of those axes, I'm met with the door interlock alarm. For added safety, whenever we work inside the machine's work envelope, we always want to make sure that we turn the rapid override speed to 0. Of course, in case of emergency, we can always press our emergency stop button. This will kill power to the spindle and the X, Y, and Z axis motors, completely immobilizing the machine. CNC machines typically operate in the Cartesian coordinate system. This means that every movement point can be defined with an X-axis, Y-axis, and Z-axis value. Let's see an example now of the machine moving in each of the axes, starting with the X-axis. Moving in the X-positive moves the table to the left, and in the X-negative, the table moves to the right. In the Y-positive motion, the table comes towards the operator, and in the Y-negative direction, it moves away from the operator. For the Z-axis, we have Z-negative moving the spindle downward, and Z-positive moving the spindle upward. Next up, we're going to talk about our workpiece setup. We need to make sure that when we place a piece of material into our vise, it's flat and level and in a repeatable position. In order to make sure that our workpiece is laid into the vise so that it's flat and at a height that we want it to be, we lay the workpiece on top of what's called parallel bars. Now, these are optional depending on the part program, but in this case we'll use them. Now, before we go ahead and lay the workpiece on top of the parallel bars, we want to make sure that there's no chips or any type of foreign debris on top of the parallel bars or on the bottom of the workpiece. Now that the parallel bars have taken care of our Z-axis repeatability, and the fixed jaw on the back of the vise here has taken care of our Y-axis repeatability, we need to figure out how we can control our X-axis repeatability. And to do that, we'll use a square head set to a known length. We'll place it up against the workpiece and bring it in until we make contact with the fixed end of the vise. Now that we have our workpiece located, all that's left to do is to tighten the workpiece into the vise. Now that we have a workpiece positioned into the vise, we need to make contact with it with a tool that's being held by the machine's spindle. Now, one of the preferred tools to do this job is what's called a touch probe. The touch probe is a tool that you see here. It has a very precision-made sphere at its tip, which measures exactly 0.400 inches. That's going to be important now in a moment. We need to tell the machine where our part origin is from our CAM program. Now, in this case, the part origin is going to be at this corner of the workpiece, and our Z origin will be at the top of the workpiece. The first work coordinate axis that we're going to define for our work coordinate offset will be our X-axis. This will be done by moving the part over until we touch the part off the tip of the probe. Now, you'll notice when the part makes contact with the probe tip, a small light will illuminate within the probe. Now that we've made contact with the side of our part using a touch probe, we need to update the controller with this position, which is going to represent our work coordinate offset X position. Now, we do this by going to our work offset window, making sure that we're in the G54 section, and that we've highlighted the X-axis. Next, we want to teach the controller of this position and confirm that we want to do so. Now, as we mentioned earlier, the diameter of the probe tip was 0.400 inches, or 400 thou. In order to get the center of the probe in line with the side of the part, we need to remove half of that value. So, in order to remove that value, or move the probe tip in the positive direction half that value, we need to add an increment input of 0.200 or 200 thou, and then just input that value. Now we'll repeat the process for our y-axis. In our y-axis, we want to remove or add a negative 200 thou to the value, because the tool will have to be brought in the negative y direction. For our z value, because we used the tip of the touch probe, which is where we measure our tool length offset, we don't need to add or remove any value. Now that we've completed our tool length offsets and our G54 work offset, we're ready to run our part program.